It's bright and early, so I think I'm going to start with a bright note as well. And let's talk about smallpox, which is one of the most deadly diseases that we've ever encountered as a species. That is until about 1798, when Edward Jenner developed the first vaccination. And then 200 years later, we were able to eradicate smallpox at a global scale. So that is a massive win for humanity. And nowadays, we have vaccinations for over 25 different diseases, and by the time you're 14 in the UK, you will have had at least 20 injections or vaccinations, which has become our most effective defense against a whole variety of infectious diseases. And it works by injecting you with a small dose of the disease, not enough to make you sick, but enough to trigger your immune system to simulate it, to start to recognize that disease as danger, and to start building defense against it before you actually come into full contact. And that's where we can draw a lot of parallels with practices of chaos engineering, which is a discipline whereby we use controlled experiments to inject failures into our system deliberately in order to uncover unknown failure modes, so that we can hopefully uncover them in time and give ourselves a chance to build defense against those failure modes in our system before they actually happens in production, where it's just going to manifest itself in like wildfire. And we do that by building understanding of how our system actually fails under those failure conditions. And over time, by building defense against different failure modes, we can start to build confidence in our system, in its ability to withstand those turbulent conditions that it's going to find itself in production. So my name is Yan Cui. I'm a principal engineer at a company called The Zone. I'm also an AWS Serverless hero. And for those of you who haven't seen The Zone, we are available in Germany, and we often call ourselves Netflix for sports, because we have a very similar business model to Netflix in that we give you an affordable and subscription-based platform for watching sports, both live as well as on demand. And we support a huge number of different sports and leagues all around the world. In fact, recently, we just acquired the rights to stream Italian football, both Serie A and Serie B. And that's why we opened up in Italy just 2 weeks ago. And we are going to go to the US pretty soon with offerings of boxing matches on our platform. We are available on more than 30 different devices. And at peak, we have over 500,000 concurrent viewers on our platform. And I'm also hiring right now in both London, Leeds, as well as in Amsterdam. So I've been reading, so whenever I go online to read about chaos engineering, I often find blog posts with titles like breaking things on purpose, or the joy of breaking things, or joy of destruction, and so on, which really worries me because it puts so much emphasis on breaking things, and it's easy to conflate the act of injecting failures with the payback. In the same way that when we have those constructive arguments with our colleagues at work, the argument itself is not the reward, or at least it shouldn't be. And if all you hear about is the argument, then it's easy to forget why we're having those constructive disagreements in the first place, which is so that we can challenge each other and hopefully arrive at a better solution at the end together. Instead, when I read all these blog posts and all these headlines, you get a sense of almost of a cavalier attitude towards breaking things in production, which is not what we actually want. And whenever I talk to people like Colton or Russ Miles or Nora Jones, people that are actually doing chaos engineering in production at scale, the sense you get from those guys is this overwhelming sense of meticulous planning, the whole sort of focus around culture and education, and most of all, an aversion to having another experiment gone wrong and have people talk about them in conferences about how badly they screwed up in production. Because the point is to learn how your systems fail before they actually happen in production, not to actually break things. So when you can learn about how your system failed, then you can start to build defense against those failure modes when you still have time. Even though breaking things probably sounds a lot cooler, so all these headlines you see, which is why they're always there. But when you go to principles of chaos.org, what you find is a very well-documented guide on how you can start doing chaos experiments yourself in your organization with 4 simple steps that anyone can follow. Step 1 is you want to define your steady state, or in other words, what normal looks like for your system. But if everything's on fire all the time, then you don't really have a steady state, and you're not ready to start doing chaos experiments yourself. In the same way that you wouldn't give someone a vaccination if you know their immune system's already been shot to bits, and giving them that injection, you're just going to make them even worse. But if you do have a steady state, you know what normal looks like, then you can start to design scenarios and hypothesize how your system would behave. And if you're going to run experiments in production, then you should have a very good confidence that your system is actually going to be able to withstand those failures. You should, by all means, explore those scenarios whereby you just have no idea what's going to happen, and they're great for learning, and they're great for identifying weaknesses in the system very, very quickly. But maybe you don't want to start doing them in production right away. Instead, you should try to run those scenarios in an environment away from production where the stakes are a lot lower. Maybe somewhere like a staging environment. And for experiments that actually graduate to production, they should be very carefully considered and very carefully planned and executed. And as I mentioned already, you should have a very good degree of confidence in the system, in its ability to be able to handle those failures correctly. And you get that confidence by running those experiments repeatedly in an environment away from production where, again, the stakes are a lot lower because we don't want to be breaking production. Just as the goal of vaccination is not to actually give you a disease, the goal of a chaos experiment is not to actually take down your production environment either. And if you know something's going to break in production, just don't do it. Right? If you know something's going to break, you should go ahead and do it anyway. Then, for starters, you haven't learned anything you didn't know before going into it. And also, you're just going to make your users angry because you've actually impacted their user experience. In terms of actually injecting those failures, the most important, or the best well-known tools for doing that is Netflix's Simian Army, which is available as an open source tool. And the engineers at Netflix also written a very useful guide that you can download for free from O'Reilly, I think. And they talked about more than just the technical side of things of how to do failure injection, but a lot on the social aspects, how you communicate, how you organize teams, and how you educate people about what it is you're doing, and how do you plan and execute those experiments. And the guys from Gremlin, who's got a booth outside, they've also done a very good job. So Colton, the company, one of the founders of the company, has brought a lot of his experience doing chaos experiments at Amazon and Netflix, and took those experiences and make it available as a commercial tool that people like you and me can start to use to run experiments in our own environment, in our own companies. So when you run an experiment, you're looking at the dashboards, making sure that all the metrics are looking fine. And then at the end, you want to go through all your metrics even deeper to look for evidence whether or not your steady state was impacted by the failures that you injected during the experiment. And if you were able to identify weaknesses, then great. Now you have the time to actually put in the engineering effort to fix those failures, to fix those weaknesses before those failures actually happen in production for real. So the key thing here is that those experiments need to be controlled because we don't want to hurt production. So how to go about keeping those experiments under control? One of the most important things you could do is to make sure that whatever it is you're doing is well communicated to everybody involved. So if you're going to run an experiment that can potentially impact services that's operated when run by a different team, then you want to make sure that they're aware of the experiments that you're going to run, and that they're OK and they're ready for the experiment itself. So it should never be a case that I come into the office one day, and then I look at my dashboard and everything is red. And then when I look into the metrics deeper, it turns out that you're running some experiment without telling me, and it should never become as a surprise like that. Which brings us to the timing of those experiments, which you definitely want to run during office hours when people are in the office and they're ready to deal with any unexpected fallout for when those experiments go wrong. And when you have important days coming up, maybe like a launch of a big new TV series on Netflix, then you also want to avoid those launch days as much as possible. There's time for taking risks for the sake of learning, but then there's also time for just common sense and avoid taking any unnecessary risks. And last, probably most importantly, containment and blast radius should always be front and center of your thinking. And that's especially true if you plan to run experiments in production, because again, the point is not to actually hurt production. So you want to do the smallest amount of change necessary in order to prove or disapprove your original hypothesis. and that you should have a rollback plan ready just in case something goes wrong that you didn't expect, so that you can stop the experiment as quickly as you can, and then as soon as those key performance metric has been impacted unexpectedly. So you hear all these big companies like the Amazons and Googles and Netflix of this world talking about how they run experiments in production all the time. But it's worth remembering that we are not Google, at least I am. I'm not. And even those companies, they didn't start running those experiments in production right away. There's a lot you can learn by just running experiments in an environment away from production, like in a staging environment. And that gives you the chance to get used to the practice and the rhythm of planning experiments, to executing them, and to communicate with different teams and educate them about what it is you're doing and why you're doing it. And Russ Miles, he often talks about how chaos engineering is not just about stress testing your infrastructure either, and the social side of things is just as important. In fact, one of the most important lessons I've learned from Russ is that when you're talking to business users or non-technical users, don't even mention the word chaos. When you're going to the business and start talking about chaos and talking about breaking things in production, of course it's going to make them nervous. So instead, you should call it what it is, which is continuous resilience testing. And when you frame what you're doing in terms of what it is that you're trying to achieve, rather than what it is you're doing to achieve that, it makes it a lot easier for the business to understand what it is you're doing and to support you in your endeavors. And for the rest of this talk, I'm going to focus on the technical side of things with emphasis on how to apply those practices to the serverless paradigm. So I already mentioned the Simian Army tools, which contains a number of tools within that, including Latency Monkey, which allows you to inject artificial delay to an API to simulate what happens when some API that it depends on is slow. You have Chaos Monkey that can queue an EC2 instance randomly to simulate the infrastructure failures. You have Chaos Gorilla that can queue an entire availability zone in AWS to simulate what happens with an availability zone-wide outage. And then you also have Chaos Kong that can queue an entire AWS region to simulate region failures. And I've also seen quite a few different attempts at wrapping the logic of Chaos Monkey into a Lambda function so that you can exercise those Chaos Monkey logic without having to run a server yourself. But what I'm really interested in is how can I take the same learning, the same practices and principles of chaos engineering and apply that to my serverless architecture, whereby there is no server, at least no server that I can access and I can control, and therefore there's no server that I can actually queue with one of these tools. But then chaos engineering is not about killing servers. It's about identifying weaknesses before they manifest in system-wide aberrant behaviors. And killing server is just what we do in order to apply those principles in a setting whereby the most likely failures I'm going to experience are infrastructure level, where the EC2 instance itself will fail. And we shouldn't confuse the principles with the actions that we do in order to apply those principles. And having worked on a couple of non-trivial serverless architectures, including one when I migrated a social network to run pretty much entirely on serverless, one of the things I learned was that there are just way more inherent chaos and complexity within a serverless architecture. For starters, you end up with a much smaller unit of deployment, which is great for many, many reasons that I'm not going to today, but you also end up with a lot more of them, which means now there are a lot more boundaries that you need to harden. Before, you can do a lot of the sort of hardening around boundaries of a service, a container, or EC2 instance, but now you have to do them on an individual function level that makes up your entire service. And for people that are building things with serverless technologies like myself, we want to get away from having to manage servers at all. In fact, we want to get away from the whole competency involved around how do you manage and run a cluster of machines. So we tend to use a lot of managed services provided by the Amazon and Google and Azure of this world. And the thing about that is that each of those services that we use and we depend on has got its own set of failure modes. Some of them are documented, sure, but many of those failure modes are not documented because they're tied to implementation details. And even for the ones that are documented, you probably don't have a way to really verify those documented behaviors until something actually goes wrong. And then for every single function, there's also a whole bunch of configurations you need to make sure that you do correctly, including permissions, including timeouts, and so on. So that just means there's a way more opportunity for you to misconfigure something. And everything the platform does for you, from scheduling container, to scaling, to polling kinesis, to polling SQS, to retrying failed invocations through a Lambda function, they all have their own failure modes as well. And again, those failure modes are often not documented because they're tied to implementation details and are typically prone to change without notice anyway. For example, if an outage happens that prevents Lambda from being able to process events from kinesis, there's really not much alternative that I can, or at least not much meaningful alternative that I can do apart from just wait for AWS to fix the problem. Because I can't just say spin up a whole bunch of other Lambda functions from a different region and start processing events where the first region failed. Because the state of the poller itself, the whole thing is a black box. The state of the poller is not accessible to me. I can't just put the same logic into a normal, say, node application and run it inside a container somewhere else. But even with that said, there's still a lot of weaknesses in my own code, in my application layer, and how my code deals with its own dependencies that we can identify and with experiments. So for example, maybe we've misconfigured some of the timeouts when we're talking to some third-party services, or maybe we're missing some error handling, or in cases where we can use a fallback when, say, DynamoDB is having an issue, maybe we're not doing that correctly. And one of the most common issues that I run into in production tends to be latency or performance related. And they can be symptomatic of a whole host of other underlying issues. It could be AWS having a network outage or some just general networking issue. It could be that I'm talking to some overloaded server, or I'm just being unlucky and hit a server that's having a really long garbage collection pause. Oops. Hilton Hotel. So how can I run experiments to detect whenever I have got those kind of underlying problems? Well, I can start by defining my steady state, and I have to decide what metrics make sense for me to monitor with my particular system, which of course depends on whatever kind of system that you're building. But some common good candidates include the tail percentage latencies, like 95 or 99 percentile, or maybe in the case of large systems with a lot of throughput, maybe you want to go to 99.99 or so on, as well as error count or the percentage of requests that you're able to complete successfully. And now that I know what metrics I should monitor, I can go about hypothesizing how my system should behave, or rather would behave, given some failure condition. And there's a couple of things that we also need to understand about our serverless application as well. For example, when you're building APIs with API Gateway and Lambda, API Gateway has got a hard limit on integration timeout of 29 seconds. So even though your Lambda function can run for 5 minutes, API Gateway is going to time out after 29 seconds. So one of the first things you have to think about is, well, does it make sense for me to have a Lambda function with anything more than 29 seconds as timeout? Another thing to think about is the effect cold starts has on your Lambda on the response time. So imagine a setup where you have two APIs, both of them implemented with API Gateway and Lambda. The first one calls the second one, and you know the second Lambda function has a timeout setting of 2 seconds, but the actual response time you can experience from the first function can be a lot longer because of the effect of cold starts. And also, sometimes the API Gateway itself can add some additional overhead to the end-to-end response as well. Even though most of the time is talking about sub-millisecond, I have seen that the overhead go up as much as over 100 milliseconds. And in microservices, the rule of thumb is to use very short timeouts whenever you're talking to some external, some other API. And the goal of your timeout strategy should be to give your HTTP request the best chance to succeed, but not without running the risk of causing your calling function to be timed out by Lambda, so that your invocation itself or your function itself will also error and cause the error to propagate up to your caller. And that's where I find choosing the right timeout configuration here is quite tricky. If I'm making a call to another API and I'm using a very short timeout, then I'm not really giving that request the best chance to succeed. At the same time, if I'm giving a lot of time, then I potentially run the risk of causing my function to be timed out by Lambda. And this gets a lot worse when you're making a number of different API calls as a part of your function. For example, if I've got a Lambda function that is calling DynamoDB to read some data, perform some business logic, and then I'm going to call DynamoDB again to save the changes back. And then I'm also going to call Kinesis to publish some event so that other systems can react to this state change that I've just introduced. Then I need to consider how much time I can give each of these API calls. I've seen two common approaches to this, and both of them have got their own shortcomings. The first approach is, suppose I've got a Lambda function that has got a timeout of 6 seconds itself, and I'm making 3 API calls. So I'm going to divide my 6 seconds equally, so that every single API call I'm going to make has got 2 seconds to complete. So in this particular case, even though overall I have got enough time to complete all 3 requests, but the second request took longer than 2 seconds, so it got timed out. And in this case, I'm not giving my request the best chance to succeed. Another approach is a bit more optimistic in that if I've got a function that's got a 6-second timeout, then I'm going to give every single request 5 seconds. And in this case, even though individually none of those requests took so long that it got timed out, but together they still took longer than the 6 seconds that I have for my Lambda invocation. In this case, it's caused my Lambda function to be timed out by Lambda, and then that error is going to propagate as a 503 to my caller. So instead, what I propose is that we set the request timeout dynamically based on how much invocation time we actually have left in the current invocation, which conveniently we can actually find out from the context object that every single invocation has. Whenever you invoke a Lambda function, you have the invocation event itself, as well as the invocation context. And with that context object, you can find out how much time you have left with a single method call. In that case, what I can do is I can always reserve some time right at the end so that I can do some recovery if things doesn't get timed out. And then for every single request I have, I'm going to give it as much time as I have got left in the current invocation, minus the amount of time that I'm reserving for recovery steps. In this case, every single request was able to complete together because together they took less than 6 seconds, minus the amount of time I have reserved. But then if one of them took too long and got timed out, then at least I've got some time at the end where I can apply a number of recovery steps, including I want to log the timeout incident with as much context as possible, including what was the service I was trying to talk to, what timeout value did I have, and any correlation IDs I've collected so far, as well as maybe the request object as well. And I also want to record the timeout incident as a custom metric so that I can monitor that on my dashboard. And in some cases where I can use a fallback value instead, or maybe some sensible default, and that's actually a pattern that's been baked into Netflix's Historics library, which I'm not sure if they still use anymore because now that they've moved into the whole service mesh world. So in this case, if I'm reading something from DynamoDB and that got timed out, then do I have some cache value from previous response? Then if I have, then maybe I can return that instead. Returning stale data is probably better than not returning anything at all. Or maybe I can return some default value where it makes sense. And that's what happens when you go to the Netflix homepage, whereby they try to load your personalized rail based on your watch history and your preferences. And if those requests fails, then they try to return you a cache response that if it has on a server. If not, they can also return you a default rail that gets returned for any new user on the platform. And as you can see, I have a pretty wide diversity of different movies that I watch. So that trade-off makes sense for the Netflix home screen, but it might not always make sense when you say trying to return someone's bank balance. Maybe you don't want to return the default value of 0, because next thing that's going to happen is they're going to freak out and they're going to call your customer support. So even though this trade-off of precision for availability makes sense in many, many places, you still need to remember that the user experience is the most important thing here. And how do we go about actually injecting failures into our serverless architecture? Suppose you've got a setup where you have 2 public-facing APIs. So those are APIs that are used by your mobile or web client directly. And they're talking to some internal API. And all of it here is implemented using API Gateway and Lambda. And your hypothesis is that your public or user-facing APIs, they handle timeout with your timeouts from your internal API gracefully. What you can do during an experiment is you can inject latency into the HTTP client that's used by your Lambda function to talk to your internal APIs. So this can review any weaknesses that you have in your Lambda function implementation there that handles the timeouts or slow responses from your internal API. And it should also apply the same techniques to other third-party services that you depend on. For example, if you're talking to DynamoDB or Kinesis and so on. And during an experiment, you can also inject latency into your AWS DK, and again, to make sure that your Lambda function is handling slow responses from AWS services that you use. In terms of the blast radius for this experiment, because you're only touching the public-facing APIs, so the blast radius is fairly small. It's limited to between that particular API or that Lambda function with the client, with your mobile and the web client. So with a blast radius like this, you're not going to cause any massive cascade failures in the whole system. But then you can also broaden your hypothesis to check, does all my APIs, public APIs that depend on this internal API, are they all handling timeouts gracefully? And if this internal API is having some problems, is it going to cause cascade failures throughout the whole system? So another reason way you can inject latency is you can inject latency into the internal API's Lambda function directly. So this will have the same impact as if you were to inject latency into the HTTP client for all the Lambda functions that are residing in the public-facing API layer. And of course, in terms of blast radius, now you're talking about potentially causing cascade failures. And that's why you want to run those experiments to prove or disapprove your hypothesis that slowness in the internal API can cause the cascade failures in the whole system. But of course, having a large blast radius means it's now potentially quite risky. And since the point is not to actually hurt production, so maybe you don't want to be running those experiments in production right away, at least not until you've got very good confidence in all of your public-facing APIs in their ability to withstand those kind of failures. However, this kind of experiment can actually be very effective at weeding out weaknesses very quickly. And it's a type of exploratory testing that I think you should really be doing in environments outside of production. And for a different reason as well, that I typically find that we are not priming developers to think about failures early enough, especially during development of a new feature, a new system, where you spend months working against a dev environment where there's minimal load. You almost never see slow server responses or any errors. And then the moment you release it into production, you find yourself in a whole different territory. And I find that we are not programmed to think about those turbulent conditions that our system is going to find itself in production, because we're just not exposed to those conditions on a day-to-day basis while we're developing the system. And in psychology, there's this technique called priming, whereby we can subtly manipulate the way someone thinks and behaves by repeatedly giving them the same stimulus. So when Facebook was trying to get into the Asia market, where network bandwidth was much more limited, so they had this whole motion of running 2G Tuesdays, whereby on Tuesdays, they would turn the office Wi-Fi bandwidth down to simulate what 2G connection looks like, so that as a developer working on Facebook, you're constantly exposed to how Facebook looks and feels when it's being run on a 2G connection. So naturally, you start to optimize your application for those kind of environments, so that when you go to when Facebook does go to Asia market, you'll be ready for the 2G connections that your customer is going to be using Facebook on. So this kind of experiments that can potentially have a large blast radius might actually be a very useful tool when you run it constantly in, say, your dev environment, whereby potentially, say, 1 or 3% of all requests would be slow, or maybe 1 or 3% of requests would have error instead of a successful response, so that you make your dev environment better resemble the kind of worst condition that you should expect your system to survive in production. And of course, your web and mobile client is also a very important part of the system, and they should be tested as well. In this case, you can also apply the same technique, but to inject latency into the Lambda functions in your public API layer, so that you can just test your mobile and web clients' handling of slow responses from those public APIs. And in terms of blast radius, again, it's just going to be between the public-facing API as well and your mobile and web client. And you can also inject latency directly into the HTTP client that you use for the mobile and client application as well. And during the experiment, you're going to be looking at a dashboard, making sure all the metrics are looking OK, and then putting a stop to the experiment as soon as you see key performance metric has been impacted. Again, this is super important when you're running those experiments in production. And afterwards, you're going to go through a lot more metrics and dig deeper and see whether or not your steady state was in fact impacted by those failures that injected during the experiment. So how do we then actually inject those latencies into our Lambda functions? If you're talking about static languages like Java or .NET, then you can use a static weaver like AspectJ or PostSharp. But for dynamic languages like Python and Node, you can also use wrapper libraries as well. And during one experiment, I wrote my own HTTP client library, which has got a simple method that allows me to inject some latency based on a configuration object that tells me whether or not to enable latency injection, as well as how often I should do it. And then I'm just using Bluebird's delay function to add some artificial delay, which is randomized between the min and max delay that I have configured. And to make an actual HTTP request, you use this request function and passing in an options object, which can include that configuration object, which ultimately is coming from SSM Parameter Store, which is a service that Amazon announced in 2016. That's part of the EC2 Systems Manager. And in this case, when my function runs, it loads the configuration from SSM Parameter Store. And in this particular experiment, I really wanted to see latency being injected. So I increased the probability of a latency injection to 50%, of injecting a latency somewhere between 100 milliseconds and 5 seconds. And when I hooked up my function with X-ray so that I can see the traces of what's going on, I can see that in one invocation, no latency was injected, so the HTTP request completed in 60 milliseconds. But on a different invocation, you can see that 3.4 seconds was added to the HTTP request because of the configuration that I have. So that's all well and good for basically an HTTP client with just essentially one function. What do you do with something like the AWS SDK, where you can't really feasibly create the wrappers for every single client library there is? So in this case, you can apply a very similar approach to Bluebird's promise by all factory function. And in this case, I've got a really badly named injectable all function, which takes the AWS SDK client object, and then introduces an async variant for the functions, which takes in an instance of that configuration object we talked about earlier. And I can see that in one example, I was able to inject, say, 1.4 seconds to the GET request to DynamoDB. So all of that proof of concept is available on GitHub, that you can go and play around with that. But we don't have to stop our experiments at just doing latency injection either. We can also inject other types of errors, especially, for example, when you're, dealing with DynamoDB. One of the most likely runtime exception you can run into is the read or write throughput exceeded exception from DynamoDB. So, and I find that most of the time we're not, the list of code that I've written and I've seen are not protecting against those exceptions when it's, it's not handling those exceptions. So one of the things you could do is apply the same technique and inject those errors when you're talking to DynamoDB through the AWS SDK client. Another particular error that's specific to Lambda is what happens when your function is throttled at runtime, and the behavior that can be very erratic and hard to predict. So one of the things you could do as an experiment is, during an experiment, I can artificially change the concurrency setting for one particular function so that the maximum concurrency for that particular function is below what it's currently running at, so that I can simulate scenarios when that particular function has been throttled by Lambda, because I have the scenario will be that I have exceeded the regional limit for concurrent executions for Lambda, and that particular function is now being throttled. And then I can simulate what happens to the rest of my system when, say, that particular function is invocations are being throttled. So the one message I want you to take away from this talk is that failures are inevitable regardless of whether or not your service actually runs inside a EC2 virtual machine or a container or inside a Lambda function. And the only way that you can really truly know that your system is resilient against those failures is by testing it through controlled experiments. And through these experiments, we can learn about how our system actually fails and its weaknesses, so that we can then improve improve its resilience when we still have time. That is, of course, unless you just jump the gun and go ahead to production and run some really risky experiment and break the whole thing, in which case you can be sure your stakeholders never going to let you go anywhere near production with your fancy chaos experiments ever again. So maybe just don't do that. And with serverless technologies like AWS Lambda, there are just a lot more inherent chaos and complexity. And if anything, there's just even more need for us to start identifying those weaknesses early, by applying the principles of chaos engineering and vaccinating our serverless architecture against failures. So my name is Yan Cui, as I mentioned already. I work on sports streaming, and I'm hiring in London, Leeds, and Amsterdam. So if it sounds like something you want to work on and you want to do some fun stuff with Lambda and serverless, then come talk to me afterwards. Thank you very much.
Thanks, Juan. We've got a few minutes for some questions. Are there any questions?
One question regarding when or how feasible is it to run chaos engineering on a deployment pipeline? So instead of just having something, preparing a day to run some experiments, to deploy a new service or whatever. Sure. And put some chaos there, see how it behaves, and if it doesn't behave as expected, roll back to the deployment.
Yeah, you could. I guess if you're at Netflix, you're probably doing that automatically already. But like Corey mentioned in yesterday's keynote, there's quite a number of different maturity models. If you're at Netflix, you're probably at that point where you're automating that as part of your deployment pipeline. You're doing all these canary deployments. You're also doing chaos experiments as part of your pipeline, so that by the time it gets to production, you already know that it's resilient, and because you do this constantly all the time. But for most companies, at least for my current company and all the ones I've worked in the past, we are nowhere near that level of maturity. So we are very much still in the stage of where, okay, we're starting out, and we are trying to do those with a conscious effort of, we're going to take some time, to run some experiments, and we're going to see how our systems behave, and then we're going to go back, and then we're going to fix problems. I would love to get to the point where everything is automated. It's so mature in the whole company in terms of how we do it, and everyone understands why we're doing it as well. But to answer your question, it is feasible, and I'm sure people like Netflix and Amazon are doing that already. But for most of us, we're just not at that level of maturity yet.
Thank you.
Another question there?
So we are talking that chaos engineering should be done on the production. But then why don't we think about the staging environment, which could be quite similar to production, and then in that way I think we could also take more risk rather than doing it directly in the production. What is the difference?
As I mentioned already, you should definitely run them in staging and even in development as well before you even get to production. Production is the holy grail. You want to run those tests in production because doesn't matter how much you try, you're never going to fully replicate production. Production is production. The data you have, the scale you have there is never going to be fully replicated in another environment as much as you can try. But that said, yes, I agree that you should definitely run experiments in staging and learn as much as you can away from the production environment. And you should only go to production when you're confident that your system is going to be fine. The idea is that I've done it so much now in staging and everywhere else, I know my system is going to be fine. At least I'm like 95% sure it's going to be fine. And then production is where I really know for sure. That's where I get to 100%. But no, you shouldn't go straight to production. That's not the idea, because we don't want to be taking unnecessary risk by running something in production where we have no idea what's going to happen.
So I run an obnoxious number of Lambda functions, and as I start looking at how to inject failure in this, increasingly it's less about breaking my own code and more about, it crosses a boundary across the shared responsibility model. Now it's, okay, how do I inject failure into Amazon native provided services? There's a very thin line there that it's easy to cross. I mean, so far the only solution I've found has been running a bunch of things in US East 1 and waiting. The problem is you can't schedule those things. It's a matter of, did I get lucky? Did Dynamo crap out today? How do you, I guess, get past a point where you're able to start doing this intentionally rather than accidentally, and or not get a panicked phone call at 2 in the morning from someone in Amazon screaming, turn it off, turn it off, turn it off? It seems like it's a difficult thing to test.
You're absolutely right. I don't know if you wrote it or someone wrote it. I remember reading a blog post that about the best chaos experiment you can run is run in US East 1. Which is why most of the failure that I actually test, I do it inside the AWS DK. So I simulate those failures in the AWS DK. Another potential thing I do is if I want to find out what happens to my function when DynamoDB just completely out, I just disable the function's access to DynamoDB. So I can say, what happens if my function just can't talk to DynamoDB at all, not even getting some throughput exceeded error, just completely out. Then I can just temporarily disable its IAM permission to talk to that particular service. You're going to get a very specific error back. So if you're handling that specific error, then that's kind of, so it validates your test. But otherwise, no, the only thing I could do is by injecting things into the AWS DK layer, which, as you can imagine, is not exactly foolproof. There are just many scenarios that you can't test, and at some point you just have to hope that Amazon is doing the right thing, and then try to build resilience by having redundancy in the layer above. So putting the redundancy onto the multiple regions and have some kind of active setup instead. That's the best I've come up with so far. Thank you.
Thanks. We got a couple of minutes for another question, maybe a couple. There you go.
Okay, cool.
Thanks
well, you can
much.
find me around the hall anyway, so just come and talk to me, especially if you want to join us.